everyone, and welcome to this edition of 30 Mechanical Minutes, virtual content for real-time professionals. My name is Doug Picklick. I'm the editor of HPAC magazine, and today we're going to be talking about heat pumps, but more specifically about inverter technology and flash injection into compressors to get hopefully to get a better understanding of what all this talk is about. First, I'd like to thank our sponsor for today's 30 Mechanical Minutes, and that's Olympia Splendid, manufacturers of the through-the-wall, wall-mounted Maestro heat pump solution, along with other heating and cooling solutions. Thank you very much, Olympia Splendid, for your support. Okay, I'm joined here today by two HPAC magazine contributors, Ian McTeer and Gerry Wagner. Hello to you both.
Hello.
Hey guys. Hey everybody.
Hello everyone.
Ian, for those of you who may not know, has been a long-time HVAC writer with the magazine and has over 35 years of experience in the industry. And Gerry has been contributing to HPAC for a couple of years now, providing us with his duct-free zone articles. And Gerry's also the Vice President of Business Development with Bathica. Gentlemen, thank you again for joining us today. I'd like to jump right into the topic here. I see we've got over 140 people joining us here today, so we're really happy to see everyone here with us. So, heat pumps, they're a hot topic in the industry, with the push towards electrification as countries around the world are committing to reducing their greenhouse gas emissions. Governments are actively promoting heat pumps through incentives for homeowners, and the mainstream media is even raising their profile by doing their part to educate consumers about what they are and why they can make sense for efficient space heating and cooling. Our audience today of mostly HVAC contractors have been exposed to heat pumps for years, but we're hearing more and more about inverter technology in heat pumps, and I guess what we call cold climate heat pumps that are driving even greater efficiencies and allowing us to operate in our Canadian winters. So Ian, I'm going to begin with you, and I'm hoping you can provide us with just a brief description of what an inverter is and how an inverter compressor operates, and what makes it different from a conventional non-inverter driven heat pump.
Yeah, sure, Doug, thank you. For as long as I've been involved in the industry, we've been looking at ways to improve comfort and reduce electrical consumption, that sort of thing. And we've done it by largely mechanical means, unloading devices and compressors. We've used two-step compressors, two-stage compressors, dual compressors, that sort of thing. And, we want to improve the comfort for the end user and reduce energy consumption and have benefits like better humidity control and all the time using fewer watts while only partially loaded. So, for as much as the mechanical method worked reasonably well, an inverter does a much better job. An inverter drive takes the incoming AC voltage, converts it to DC using a rectifier. So the resulting DC voltage powers the inverter circuit that produces an AC voltage at variable frequency. So the compressor motor speed is controlled by the AC hertz delivered to it, depending on the heating or cooling load conditions. So, a combination of sensors and smart thermostats and that sort of thing makes all the decisions and decides what speed the compressor should run at based on the load condition at the time. So I'd have to say that the inverter drive compressor is probably one of the most significant advances in the HVAC industry, especially residential products going forward. I think we're going to see a lot more from our inverter drives in the future. Doug?
Yeah, so variability of speeds is kind of a key to how the inverter operates.
Yeah, that's right. We use the speed of the compressor to control the capacity of the
Right.
system as opposed to unloading and that sort of thing that we used to do in the past.
Okay. Now, Gerry, I know you've made this bold statement I've seen it in print a few times, and I know you've said it out loud as well. But
Yeah.
here it is: the inverter compressor is the greatest invention in the HVAC industry in my lifetime. Now, we don't know the span of your lifetime, Gerry. We don't need to get into that, but I'm hoping you can tell us why you believe it's been such a game changer.
No, I'm glad to share my age, Doug. I'm 62 years old. I'm an old man, so that's I've earned the right to be able to say that. So yeah, no, I wrote my column a couple of years ago, dedicating it to the inverter compressor, and that's when I first made that statement publicly. And I think to some degree it's obvious, Doug. You know, we're talking about SEERs now in the high 30s. You know, we have a product that's 38 SEER. 38 SEER. I never thought I'd say that in my lifetime. Nevertheless, my career. And that's all a result of the inverter compressor. Low ambient heating. Now, I know today we're talking about vapor injection, which has even taken it yet to another level. But the standard, what I'll call the standard inverter compressor, bringing low ambient heating down to -5 Fahrenheit. And I apologize. I know this is a Canadian broadcast. I should be able to refer to Celsius, but please excuse me on that. But, you know, -5 Fahrenheit, guys, that's crazy. I'm a child of the 70s. I got into this industry through my father, and he used to have a joke in the boiler industry that you would never install a heat pump north of Richmond, Virginia, because back in the 70s, a heat pump quit on you at 47-degree outdoor air. It wasn't derated at that point. It was off. It was over. That's all you were getting. And now we're talking, like I say, -5 is the standard, and all because of the inverter compressor. It allows for zoning. Again, something that wasn't capable with mini splits anyway prior to the inverter compressor, where we can have a evaporator, an indoor unit dedicated to different rooms. Even the most unsavvy civilian, and I call our homeowners, our customers, respectfully, civilians, even the most unsavvy civilian, when you explain zoning to them, they want it. It makes perfect sense. Yeah, I don't want the system to be on over there when I'm over here. I like that. Do that zoning thing. So that is all capable because of the inverter compressor. Soft start technology. You know, one thing that is key with inverter compressors to point out, I believe, is that they do not start at 3,600 RPM and work their way down. Just the opposite. They start at 0, very, very slowly working their way up to possibly never even seeing 3,600 RPM full amp draw, because once it finds that sweet spot, and the sweet spot being the set point temperature, it'll go into what I call cruise control. So yeah, it's a compressor, Doug, with a gas pedal. That's the best way I've always described it. And you know, anything that you have control over the power voltage, the intake, and the output, that's a better way to go. So it's a compressor with a gas pedal.
Very good. Okay. Well, Gerry, I'm going to stick with you if I can. And
Yeah.
because I also want to talk about this flash injection technology,
Yeah,
because
sure.
I think, or also I think you refer to it as enhanced vapor enhanced vapor injection compressor. But
Yeah.
regardless, I think sometimes people think, and you kind of mentioned it, that inverter technology is what's allowing these air-to-air heat pumps to perform at lower temperatures. But really, it's this flash injection that's making the difference in what we're calling cold climate technology, I think, these days. So I'm hoping you
Sure.
could describe for us a little bit about how that works. And I know I've got something here, an image that we can share.
Oh, yeah, beautiful. Well, Doug, it's commonly called the two-stage vapor injection compressor. And I always say to call your compressor vapor injection is a little bit like calling your beer fire brewed. well, of course your beer is fire brewed. That's what brewing is. Well, of course your compressor is vapor injection. We don't compress liquid. So to be honest with you, that's kind of a marketing term. But the key is what's significant in the description and the title is the two-stage. If you look at the compressor on the screen right now, two suction ports. That should be blowing everybody's mind. You've never seen that before. A single discharge, but two separate suction ports. And that's the key to vapor injection. I'm going to bring everybody back to sixth grade science class. Remember, Mrs. Gillicuddy taught us that when matter changes state, solid to a liquid, liquid to a gas, she taught us that energy is produced. But what she didn't tell us is that when vapor changes pressure, energy is produced. And that's what's happening here. That's how we're getting heat out of, again, crazy outdoor temperatures like -33 Fahrenheit because of that second injection. There is a valve on the second injection port, which we call a vapor injection valve, which based upon outdoor air temperature and some other criteria will open. And that's what gives us what many companies call their ultra heat technology. So yeah, that's how we're scrubbing heat out of incredibly low outdoor air temperatures with two suction ports at two different pressures and scrubbing energy out of those two different pressures. So that's the key. And yeah, really, really interesting stuff, bringing heat pumps yet to another level with low outdoor ambient heating.
Okay, thank you for that. That's a history or a back to grade school science, and but it's hopefully explaining some of this for those who maybe weren't as aware. Ian, I know you have installed a cold climate heat pump in your home, your relatively new home. We talked, you've written about this actually in the magazine. So I'm hoping you can share with us a little bit about the technology's performance that you've experienced. And I know you provided me with a couple of slides, so I'm going to get those up as well. But maybe you can share a little bit about what you've done at home.
Oh, yes, Doug. This is a balance point chart. Now, this is something that we probably don't need to do anymore because electronics largely solved the problem of which unit is going to operate at what time. And we now have hybrid systems that decide whether the heat pump or a gas furnace should operate, that sort of thing. But this is a balance point chart is something we used to do in the early days of heat pumps, conventional heat pumps. That's the non-inverter, non-cold climate compressors. So what we would do is, of course, we need an accurate load calculation. So I live near Ottawa. My outside design temperature is -25°C. It does get colder than that here, but my load at design is 34,399 BTUs. So I plotted that on the chart at -25°C or -13 Fahrenheit. And I drew a line down to 65 or 18 Celsius. That's the theoretical point where no heating or cooling is required. So we call that the load line. The red line, in this case, I plotted a conventional 2.5-ton heat pump on the chart. So the manufacturer told me at 47 or 8.3 Celsius, this unit would put out 27,600 BTUH. So I plotted that at 47. And the manufacturer said at 2 Fahrenheit or -25°C, it puts out 11,900 BTUH. So I drew a line that's called the equipment line. So where the equipment line crosses the load line, you drop an arrow down to the temperature grid and you see that the balance point is 22 degrees Fahrenheit or -5 Celsius. So that's the point where second stage is going to call. That's the point where the heat pump is running out of steam and it needs some help. In the old days with conventional heat pumps, we were using electromechanical controls, and we needed to set a balance point so that the house you wouldn't get a drop in temperature. But we also wanted to make sure that the heat pump was delivering as much heat as it possibly could. So we didn't want the heat pump shutting off too early, nor did we want the backup heat coming on too soon. So the balance point chart is what helped us to determine what when that second stage was going to call. So this conventional 2.5 ton heat pump could have worked in my house, but I would have enjoyed the benefits of the heat output, but it's totally going to wreck my cooling. This unit puts out 2.5 tons on the cooling side, and we always used to oversize heat pumps a little bit. 0.5 ton sometimes was the rule of thumb. But in this case, my cooling load is only 16,000 BTUs per hour. So you can see that this heat pump would not have worked in the cooling mode at all. And we would have had humidity problems and short cycling and all the issues that go along with oversizing. So conventional heat pump then also, we're also dealing with ductwork as well here. So in order to have this heat pump, I also need an air handling system that can handle the airflow it's going to produce, which fortunately I do, but in so many cases, the airflow or the ducting situation was an issue. So if we go to the next slide, Doug, here I've used the same load, my load, and I've used my Mitsubishi heat pump data, 47 or 8.3, I'm getting 32,000 BTUs out of it. And at minus 25, I'm getting 25,600. So you can see where that equipment line crosses the load line. So my balance point is down to minus 18C. And that's just a remarkable difference. So at minus 18, I'm going to get a bit of my backup heat coming on to supplement. So both units will be running together. In a hybrid situation, you're going to, especially with a gas furnace, oil furnace, or propane furnace, that unit's going to shut off at that point. Or the outdoor unit, the heat pump will shut off and the gas furnace will take over when the temperatures are ranging lower than that, which fortunately doesn't happen too often. So essentially, I think you can see that a cold climate a heat pump just does a phenomenal job. Using the old balance point calculation, we can see a phenomenal range. You want to flip to that next slide, Doug. This is a chart we used to use in the old days where we had a staged electric furnace. So you can see that the slope on that equipment line is fairly dramatic. And in this particular case, the balance point, the point where the backup heat's going to need to come on, is at 33 degrees Fahrenheit, or what, +1 or 2, something like that. So, I mean, this is the cold climate heat pump is decidedly going to outperform this old blister. Right. So at the first balance point, you're going to get 9.6 kilowatts, roughly 10 kilowatts of electric heat to come on. That slope is then going to parallel the original slope until you hit the second balance point at 10 Fahrenheit, at which point an outdoor thermostat will bring on the last 5 or 6 kilowatts of electric heat. And that's the third balance point at -5 Fahrenheit there in this elderly drawing. So you can see that that's third balance point is beyond the outside design temperature. So there's a bit of a fudge factor in there for the times that the temperature does get a little bit lower than the calculation. So, all in all, as Gerry said, it's these cold climate vapor injected heat pumps are truly a tremendous innovation in the industry. And the sooner we can get more of them out there, the better.
Well,
Thanks.
Ian, I know you've been through a winter or two now with your system.
Yeah, second.
Comfort level.
Yeah, and it's just been absolutely delightful. And another benefit that you get from soft starts that Gerry mentioned is the units tend to be a lot quieter. My unit is actually running a bit today. You can barely tell it's running in the cooling mode. And the soft start actually reduces the lock rotor inrush current, which the utilities like to hear about as well. So, they're talking about, rapid voltage fluctuations and light flicker caused sometimes by compressors starting up in certain situations. So we're kind of helping our creaky old grid along as well by going with inverter drives.
Yes, I know, Jerry, you touched on that as well. Thanks, Ian. And I know we've been talking a lot about heating, but I know we're heading into cooling season, or we're already there in some cases. And Jerry, more recently you've written about how inverter technology actually improves the capacity of multi-zone mini split systems, where one outdoor unit can feed multiple indoor units. But the inverter technology really takes this to another level. Can you kind of explain that a little bit?
Yeah, no question, Doug. Like I said earlier, the inverter compressor not starting at 3,600 RPM, it matches the load. So whatever zones are calling or not calling, the output of the compressor matches the load at that moment in time. So that's where the great savings takes place for sure. And the basic multi-zone product, up to 5 indoor units. Now there are products that go well beyond that. We can talk super multis and even things such as variable refrigerant flow, which is clearly a different animal than what we're talking about today. But these systems do exist where you can have tens of indoor units on a multitude of outdoor units. And there's a variety of type of indoor units to choose from, Doug, right? We have, as you can see here, the standard high wall mount, which is what I have here in the studio. But there's ceiling cassettes, there's ceiling mounts, there's universal mounts, there's ducted units as well that can be completely concealed. So when you consider all the different varieties, there's an enormous amount of indoor combinations versus the outdoor multi-zones. And in some cases, many of these manufacturers actually allow for more indoor capacity than outdoor capacity. And I actually have a hard time completing that sentence sometimes because it just seems so wrong, right? More indoor capacity than outdoor capacity. But what I always stress to people is stop looking at the model number. And I know that sounds crazy, but seriously, stop looking at the model number, because especially with inverter systems, the model number is not representative of what exactly that outdoor unit can do. For example, an 18,000 BTU outdoor multi-zone can in many cases give you as much as 22, if not 23,000 BTUs of cooling and heating. So it's always best to look at the capacity chart, not the model number, because again, the actual capacity of that unit more often than not exceeds what the model number would represent.
Yeah, I think that's the point you brought home. So so people look at the fine print, I think is where
No question. And Doug, if I could just go back to one thing that Ian said about utilities appreciating inverter technology because of that soft start. My wife and I here, Patricia and I, we're about to go solar next week. 2 arrays being installed to completely take our home solar. And I had concerns about possibly, inverters, bucking inverters, so to speak. But our solar guy said, solar appreciates the inverter technology. Instead of banging that standard compressor on at full amp draw, 3,600 RPM, that soft start, as Ian said, just like the utility appreciates it, so does the solar people as well.
Ah, it's interesting. Thank you for that.
Yeah.
Okay. Well, okay, we're still talking heat pumps. I'm going to just run a couple more questions past our guys, and then I'm going to take a look at we've got a lot of activity in the chat here and some questions coming into the Q&A panel. So Ian, just quickly, we're talking about heat pumps with inverter technology, flash injection compressors. But when we're talking about these, we are talking about kind of the premium products in these heat pump lines generally. It's going to cost a little more for consumers. I think we've talked about the reasons why they make sense, but I know you still have some concerns about maybe the market readiness for this technology. You kind of voiced that. Whether that's our HVAC technicians out there who are watching this today, or just our infrastructure, as you've kind of already mentioned. But can you elaborate a little bit on what your concerns might be?
Well, yes, the cold climate vapor injected heat pump systems, especially ducted, are expensive. I know that the government has offered some help, but nevertheless, it's you're still looking at anywhere from I'd say $13,000 to $20,000, I guess, to get one installed. Now that's the ballpark figure. Don't take me to the bank on that particular one, but it's certainly more than just a conventional gas furnace, for example. Now, someone I noticed in the chat had mentioned, why would we run a heat pump in a gas furnace? Well, if everyone on my street converted to a heat pump like mine tomorrow, there's not enough electricity on this street to run all those electric furnaces and all the heat pumps. We're in Ottawa. It gets really cold here. I don't think any of the houses on my street could possibly have a heat pump provide 100% of the heating requirement on the coldest day of the year. So all of these houses are going to need some backup heating. And right now, natural gas is probably the best way to go for a backup source, to be used sparingly only on the coldest days. And it's really not going to happen until the grid is fixed, until the grid becomes more substantial and can deal with all these new electrical devices, especially charging for electric cars and that sort of thing that they want to do in the next 10 or 15 years. So it's going to take a while to get the improvements through. And I see that Enbridge is actively involved in a program where they have a hybrid. They're offering hybrid systems with involving heat pumps and gas furnaces. So for now, I mean, that's going to be the route that some consumers are going to have to take. And it's simply a matter of getting the grid up to the standard where we can utilize it fully.
Very good. And Gerry, I know you've been traveling across Canada in the role that you have, educating folks about this technology. I think clearly you're seeing a broader adoption of the inverter and the enhanced vapor injection compressor products. I just want to get some of your impressions on just how confident you are about how they're performing today, and then kind of where you see this technology heading in the next few months, and kind of based on what you've seen already.
Yeah. Well, my confidence level is beyond high because we have now gone through a number of winters with the inverter technology, and now even with the vapor injection technology. And just this past winter, where we had quite a cold spell, it seemed throughout North America, the US and Canada had a couple of weeks there where it was just absolutely brutal. Ice storms in Quebec again, and again, coast to coast. And we were just thrilled to be getting reports from coast to coast, from Prince Edward Island, from Victoria, British Columbia, and north in Canada as well, where systems were performing as sold, as designed, and just everyone singing the praises, to say the least, of the cold climate heat pumps. So the technology is working. It's tried and true. It's nothing to be afraid of at this point. And where it goes from here, Doug, wow, I'm starting to look at the finish line, so to speak, in my own career. And boy, it's just my luck, right? Just when things are really starting to get interesting, I'm going to hang in there as long as I possibly can, because I always tell people that come to my classes for the first time, just kind of wetting their feet with inverter technology and mini splits, that they're coming in. It's such an extraordinary time. You watch this industry it seems every 18 to 24 months, SEER ratings are going up. Outdoor air limitations are dropping again. And I don't see that stopping anytime soon. We're up to 38 SEER. We're going to be in the 40s before you know it. It's bizarre. You know, at some point, the utility company will send you a check every month. No, that's not going to happen. But you know what I mean. It's the sky's the limit, and the technology is tried and true. It's nothing to be afraid of. It's a beautiful thing.
Okay. Jerry, we're gonna run to some of the questions now from
Yeah.
our listeners or watchers. Thank you. So I'm gonna start. Here's a question from David. Where is the flash injection line taken from in the refrigerant circuit, and how is the quantity taken controlled? Jerry, can you chime in on that?
Well, there is a vapor injection valve, which is really, quite frankly, nothing more than a motorized bypass valve coming off the suction. And again, only activating when an outdoor air temperature drops below where that ultra heat technology, where that vapor injection is required. Beyond that, yeah.
Okay, and it's controlled like there's sensors. I mean, this thing.
Oh,
Yeah,
no question. There's an outdoor air temperature sensor, and a lot of people think that these systems have outdoor air temperature sensors so that a homeowner can press a button or look on the thermostat and see outdoor air. And that's not the case. It is one of two of the most important pieces of data that these systems utilize. You know, I don't know if Ian would agree with me on this, but what I love so much about this technology is that in so many cases, it's really older technology. For those of you who are wet-heads, and this is a Canadian audience, you're all wet-heads, you're all boiler people. This is 45-year-old technology. In the hydronic world, it's called indoor-outdoor reset, right? Where we take indoor temperature and balance it with the outdoor temperature to determine the BTU output of a boiler. Well, we're doing the same thing here all these years later with indoor and outdoor temperature to determine the running RPM of a compressor. So again, when you scratch below the surface a little bit, not necessarily new technology.
okay, very nice. Love that.
Well,
Love that.
just a quick
Yes.
second, Doug. I know that Samsung, for example, if they have a nice video on YouTube, I believe they called it their ICI technology, and essentially they're diverting a little bit of liquid coming back from the condenser, and they're running it through a plate heat exchanger. And then they have a solenoid valve that allows them to inject that, which is after it goes through the heat exchanger, it becomes dense vapor. And then as needed, it can be injected. And it looks like they're injecting it into the scroll set or into the suction line just upstream of the compressor. I believe that Mitsubishi uses a system that has what's called a flash tank, where they dump a little bit of hot gas into the flash tank, where it immediately becomes dense vapor that's re-injected into the compressor. I believe that's how it works. Mitsubishi and Samsung don't hold my feet over the fire, but from what I've read, I think that's how your systems work. That's a great idea. I just love it.
A little different. Okay. Well, when we were talking about the flash technology, I think this question came up. Why are two pressures better than one? I mean,
Well,
why?
I'm sure Ian could give a more scientific and will give a more scientific explanation. But again, two different pressures, two different energy levels. You know, again, going back to matter changing state. When matter changes state, energy is produced, but when vapor changes pressure, energy is produced. So that's why the two different pressures.
I believe that's the answer.
Yeah. Someone's asking, why do heat pumps take longer than fossil to hit set point? How do you size an inverter unit? I mean, these are.
Well, first of all, I would disagree with the statement in general that there's any issue with them being slower to get to set point. In fact, I may even suggest that that's just the opposite, quite frankly, at least up against a hydronic system. I don't know if Ian would agree with me on that, but I don't think there is no trade-off for comfort, people. I think that question suggests that somehow there is a trade-off for efficiency and to comfort, and there absolutely is not.
Okay.
Well, that in the early days of conventional heat pumps, that there was a lot of truth to that. In fact, we used to advise people to never set back in the wintertime because a conventional heat pump coming out of setback would take hours to bring the temperature up, and they heated with low temperature air. Typically, you were running at air coming out of the vents at just over 100 Fahrenheit, something like that, 105 degrees. So it would take a long time. So yeah, there was some truth to that. But the newer heat pumps, I set mine back 2 degrees C at night, and there's absolutely no problem in the morning coming out of setback. And judging by my thermostat traces, the unit brings the temperature up without having to bring on the backup heat. So 2 degrees C setback is very good, and I'm up to temperature in no time. So I believe that those days are gone. And of course, there could be problems with the system as well. I mean, I'm talking about a unit that's properly specified, installed, and maintained. Of course, that's the main thing. A dirty filter or something will, can easily hamper performance in that regard.
These are our critical statements as well that I think everyone should just acknowledge, right? I mean,
Yes.
You got to get it right on installation, right? Commissioning, what have you, and then maintain that these devices. It's just like any system.
In that question, Doug, the person asked, how do you size a heat pump? Well, again, a proper heat gain, heat loss calculation is in order. That doesn't change, right? It's the year 2023. We have to apply science to this. There's no more guesswork. There's no more excuses for guesswork. There's any number of ways to do proper heat gain, heat loss calculations. So that, to me, that's where it starts.
Absolutely. Someone asked for a comment on inverter technology compared to ECM motors. These are two different animals, yeah?
Ian, you want to take a shot at, I mean, again, to me, that's apples and oranges, but Ian,
I
it's
think
yours.
they're essentially the same, really. An ECM motor is it's wound like a 3-phase motor, and it uses essentially an inverter, and it only powers any 2 windings at a given time. The computer decides which windings it's going to power based on the feedback that it's getting. So I believe they're essentially the same. If you look at the electronics inside an ECM, I believe there's a rectifier hidden in there somewhere. But I have to apologize. I'm not entirely up on that.
Yeah, the ECMs are, you see those for fans and the like, right? But we're talking about something very different here.
Yeah, Doug, that's what kind of threw me with the question, is that it's apples and oranges as opposed to, it's a compressor and a motor. But as far as what Ian just said, if we're just simply talking about modulation, yes, they both do that. They both modulate based upon data from the environment.
Right. They both have this variability feature, which is great for modern.
Right. Their ultimate function is 2 separate things, but if the question is just simple modulation, yeah, you bet they both do that.
Yeah. Ian, maybe you can answer this, or both of you, I guess. Are they quieter starting, I guess, than heat pumps of old?
Oh, absolutely.
Yeah, big time.
That's the only word I can use. Absolutely.
Yeah, I think that goes without saying. That's this ramping up as opposed to boom. Getting going.
And I can actually throw some numbers. A typical 4-ton system is about 58 decibels. I'm talking the outdoor unit. And unless you're a recording engineer, that probably means nothing to the audience, Doug, but normal conversation, pre-COVID, no social distancing, 2 people standing next to each other, having a conversation is somewhere between 60 to 70 decibels. So it's quieter than normal conversation.
Okay. Do you get more, this is for you, Gerry, I think, do you get more than rated capacity due to the fact that you can overspeed compressor?
Well, that's a part of it. Again, just because of the modulation, the capacity range is so generous. yes, it goes beyond the stated capacity, but yeah, and that's pretty true across all the different manufacturers. Again, going back to my statement of earlier, stop looking at model numbers and start looking at capacity charts, because 9 times out of 10, and in many cases 10 times out of 10, the unit will actually outperform what the model number would suggest.
Okay, very good. We're gonna answer a few more of these. So we're going a bit over time here, folks, but I hope you're fine. The questions are pretty solid here. Ian, you kind of brought this up, but with new cold climate heat pumps, do you size for heating or the cooling load?
Oh yeah, that's a good question. Well, I sized for the heating load. I got the manufacturer specifications and I saw the heating output, and then I looked at my load calculation and I saw my cooling load. And of course, there's quite a difference there. So I wanted the BTUs on the heating side. So yeah, absolutely. Now, in the old days, the old conventional heat pumps, they used to say, well, size for the cooling load and add half a ton, which was probably the worst advice I had ever heard, because cooling equipment was often oversized in the old days, and then adding half a ton to it to try to take advantage on the heating side just left systems working very poorly, in my opinion. And quite often the air handling side wasn't adequate either. So in the case of a cold climate heat pump, yeah, you want to look at the heating output. Absolutely.
Gerry, yeah.
Oh yeah, no question. Doug, if you don't mind, I just want to go back real quickly. There was a question about why would you use an inverter system with a gas furnace? Well, I'm learning so much from my Canadian friends, specifically in the province of Alberta, where dual fuel systems are so popular. Why not use whatever the fuel is cheaper in that moment in time, where natural gas, it's coming from Alberta. It's perfect for that particular province, and many provinces throughout Canada, where we're just simply taking an A coil, putting it on top of an existing gas furnace, using an inverter-based outdoor unit, and now you have a high efficiency dual fuel system. It's a beautiful thing. So that's the reason why you would do such a thing.
Yeah, very good. Okay, we've got a few. Ian, I don't know, are you able to see the questions and answers here? Or the
I
questions?
see some of the questions, yes.
I'm putting in a cold climate heat pump together with the non-communicating furnace. Is there an interface that takes thermostat command and converts that to a signal to the condensing unit via a 4-wire communication wire? How does this tell the condensing unit what the demand is? That's out of my league. I don't know if you guys are.
Okay, well, I can sort of answer that. I originally on my system, I wanted to have a thermostat that's a smart thermostat that talked to the internet. And actually, Mitsubishi doesn't really have anything in that realm at the moment. I believe they're working on it, but I tried a system that used actually an Ecobee thermostat, which is a great thermostat, by the way.
I love the Ecobee, yeah.
And it was tied into my Mitsubishi system with an interface, and which is a 24-volt to digital converter interface. And for as much as it worked beautifully in cooling, I did have a few problems on the heating side. Several times it just there was a call for heating and the system wasn't getting it. It wasn't starting in heating mode, and the thermostat literally seemed to be confused, or the interface was confused. So I've actually abandoned that system now, and I've gone to an all Mitsubishi controller, and I'll just wait for them to come out with their smart stat. It's coming out sooner or later, I've been told.
Okay. I'm just trying to go through some of these.
I did see one come across, Doug. Someone asked the best control for that dual fuel system, and Ian had mentioned the Ecobee. I see the Ecobee so much in Canada. They're a Canadian company. It's a beautiful thing. So I see the Ecobee used quite a bit in the hybrids, what I call the dual fuel systems.
Okay. I think we've done it. I think we've addressed most of these from what I'm seeing. I think there's a bit of redundancy. So, gentlemen, I'm going to thank you very much, and everyone watching. I want to thank our sponsor again today, Olympia Splendid. Your support's greatly appreciated. For more information on Olympia Splendid, you can visit olympiasplendidusa.com. And of course, thank you to Gerry and Ian for taking your time today. I think you've given a lot for our audience to think about, and I hope we all learned. I know I learned some more here today, and I thank you guys for that. Thank you for your years of experience in the industry to be able to bring that knowledge forward and tell us why this new technology is really making such a difference for all of us going forward.
Well, thank you, Doug. Ian, great working with you. And in the background, Alex putting this all together. Thank you, Alex, as well.
Yes. Thank you, Alex and Gerry. Great.
Okay, and of course, I want to thank everyone who joined us on the webinar today. Until next time, thank you all for joining us. See you then.